Welcome. In this session, we'll explore some of the terms that are used in convex optimization. One of the first terms is a property function. And a property function is one of those constraints, right? So when we refer to a constraint, what we mean is a property must be satisfied. So what we'll say is that for any whole number I that is non-negative, a function p sub I that has a vector argument and returns a real number. So we'll define this is a property. Property is defined as, we'll simply say that this function is convex. Simply put, what that means is that we will refer to any convex function as a property function, or when we say something's a property function, what we mean is it's a convex function. And we'll index this starting at the number 1 and so on. So let's observe that, let's make an observation here. So observe that any level set of a property function, so we're writing that as a double-barreled S with an L under it. Now it's the property function at some level, and that is a convex set. And this follows directly from P being a property being convex, and the level set of a convex function is a convex set. So closely allied with this is a feasible point. And we've referred to this earlier in earlier sessions in a colloquial manner. Now what we mean is that if we're given M property functions, so let's just call those properties, okay, a point W, which is a vector that has n entries, is a feasible point. Feasible point. What we mean is that if I is a positive whole number and I is less than or equal to M, so those are some simple conditions, then the ith property of that vector is less than or equal to 0. So that says that if I is a legitimate index of a property, then that property holds for the point W. And let's observe here that the intersection of convex sets is convex, so that means the set of feasible points is convex. So observe, this is a convex set. And those observations are going to make some of our following results much easier to demonstrate. So let's take an example, which is linear properties. So we could write this as a theorem, and so what we'll do is in the notes, and you really should be reading the notes as well as watching these videos, right? So in the notes we say that for any number L that is a positive whole number such that it's less than or equal to M, and, oh, sorry, that's an N. So what this says is if we have up to as many properties as we have dimensions of our vectors, and for any full rank matrix M that has L rows and N columns, and for any constraint vector that has L entries, the set of all W such that if W is a vector with N entries, and we take the matrix, we multiply it by that vector, we subtract the constraint, and if that equals 0, that is a convex set. So here what we had was, we said that that feasible points are a convex set. Now what we're doing is we're specifically saying that if all of our properties are linear, then this is a convex set. And this can be proved, and we do so in the notes for this class. With this understanding, we can now define what we mean by a convex optimization problem. So such a problem is one that has to have a convex objective. And that is its objective, which is a function that has a vector argument and produces a real level, has to be convex. And it has 0 or more, which is to say some number M of definitely of nonlinear properties. So we'll refer to those as the PI that have vector arguments and produce real numbers. And it has, so let's put a little dot there and a dot there and a dot there, that it has a full rank matrix M, and that matrix M has L rows and N columns, and associated with that matrix is a vector, a constraint vector, which has L entries in it, and a minimizer. And the problem is, what we want to do is we want to find an optimal vector. So that's a vector that out of all of the possible vectors in the n-dimensional vector space, we want it to be a minimizer of this convex function, and we have constraints. What we have is that the property functions of that minimizer have to be less than or equal to 0, and we have the constraint that if we multiply the optimal vector by the matrix and subtract the constraint vector, that exactly equals the zero vector. So that briefly is what we mean by convex optimization. We go through it in much more detail in the notes. So a particular one that is of interest in this course is quadratic programming. And this is a slightly odd term. As an aside, while I'm writing this down, optimization often has its own distinct literature, and it's an odd little piece of mathematics because it often has its own language to it. So we're calling a problem, or most of mathematics would call a problem. In optimization, it's often called a program. So a linear problem to us is one that has a linear objective and linear inequality constraints. And then but in optimization, that's called a linear program. And so what we'll call a quadratic problem is usually called a quadratic program in optimization. So this is one where the objective has a specific form, and that is, we may have a half term, we may not. We'll just write that as the transpose of a vector times a matrix times the vector, and then we may have some additional linear term add onto that. So it's a quadratic program if it's got a quadratic objective. So that's a quadratic form plus a linear form. And if each property Pi is linear. So what that means is, let's observe here that for the objective to be convex, we need this matrix K to be symmetric and positive semi-definite. That is, and this is the way that we write it, but what we need is K has to equal K transpose, so it has to be symmetric, and all of its eigenvalues must be greater than or equal to 0. Let's briefly explore this a little more formally. What we mean is that if we have any matrix K that is symmetric, positive, definite, any constraint vector Q that is appropriate size, any matrix A whatsoever, that's our inequality matrix, that is of an appropriate size, any full rank inequality matrix that's an appropriate size, and any other constraint vector that's an appropriate size, we're saying that a constraint optimization problem, quadratic problem, is that we're trying to minimize a quadratic function such that we have a set of inequality constraints, and this matrix doesn't have to be full rank. In fact, it can often have more constraints than there are variables, but the equality one has to be a full rank, correctly sized matrix. So in summary, what we've done is we've represented equality constraints as linear equations. Our inequality constraints are specifically linear inequalities, and we're saying that a convex problem has both a convex objective function and a convex feasible set.